This is my fourth video lesson for the unit periodic table. In this lesson, we will be using table S to determine the electronegativity and ionization energy trend. So go to page 17 in your class packet. Motivation. Look at table S. What is the highest and the smallest value of electronegativity? Question 2. What do you think ionization energy means? So we will be answering these questions later on in this lesson. Learning target. At the end of the lesson, I will be able to determine the electronegativity and ionization energy trends on the periodic table by extracting information from table S. For homework, it will be number 4, Junipod, which is based off this lesson. The third exam will only be on the periodic table unit. There will be one more lesson before that exam. Electronegativity is the measure of attraction for bonding electrons only. The values of electronegativity can be found on table S for each element. The values can range from 0 to 4. The higher the value of electronegativity, it means the stronger the attraction for bonding electrons. So a 4 means very strong electronegativity, while 0 means very weak electronegativity. Check of understanding number 1. Which element has the highest electronegativity? And why do you think that's the case? So the element that has a 4 on table S is fluorine. Check of understanding number 2. Why some of the noble gases do not have electronegativity values? Notice that helium, neon, and argon do not have an electronegativity value. Why is that the case? Keep in mind, electronegativity means it's the measure of attraction of bonding electrons. These noble gases do not bond. Therefore, they cannot have an electronegativity value. Now we're going to figure out the trend for electronegativity for across the period. We're going to look at period 2 as an example. So I want you to do the same thing as you did with atomic radius. I want you to use table S and look up the electronegativity values of each element in period 2. Pause this video and resume once you've done it. Okay, let's go over the answer. So lithium is 1, beryllium is 1.6, boron is 2, carbon is 2.6, nitrogen is 3, oxygen is 3.4, fluorine is 4, and neon does not have a value. So by looking at this, the trend is obviously increasing from left to right. The question is, why electronegativity increases across a period? So in order to answer this, you need to compare the effective nuclear charge and the shielding effect. So you should know across the period, effective nuclear charge increases. So the stronger the nucleus, or the stronger the effective nuclear charge, is easier to attract the bonding electrons. And the shielding effect is constant across the period, because each element only has 2 inner electrons. Now I want you to look up the electronegativity values of each element in group 1 and figure out the trend. Once you've done it, resume this video. So for hydrogen, it is 2.2, lithium is 1, sodium is 0.9, potassium is 0.8, and rubidium is 0.8. So based off of this, what is the trend? It is increasing from bottom to top. As you can see, fluorine is the most electronegative element. These noble gases here do not have electronegativity values, so the least electronegative atom should be in the bottom left of the periodic table. The question is, why electronegativity increases going up a group? You should know by now the effective nuclear charge is constant within a group, so that means the shielding is going to play a major role here. As you go up a group, the shielding decreases because the atoms get smaller. There's less inner electrons. Since there's less inner electrons, there's less competition for the nucleus. So it's easier to attract bonding electrons with less shielding electrons or a smaller radius. The effective nuclear charge is constant within a group. Learning check number 1. Which list of elements is arranged in order of increasing electronegativity? Pause the video and resume once you have the answer. Okay, so the answer is 3. You can use the trends, but in case you forgot the trend on the day of the exam, just use table S and look up the electronegativity values of each element. That'll be the easiest way to do it. Learning check number 2. An atom of which element has the greatest attraction of 4 electrons in a chemical bond? Pause the video and resume once you have the answer. In this question, you must know that attraction for electrons in a chemical bond means electronegativity. So basically, this question is asking which of these elements has the highest electronegativity value. So if we use table S, that would be choice 4, selenium. Now I want you to graph the electronegativity trend for the first 20 elements. Assume that the noble gas have a 0 as the electronegativity value. Once you graph it, resume this video. Okay, so your graph should look like this. Now we are going to talk about the first ionization energy trend. What word do you see in ionization? You see the word ion. So basically, ionization energy means it's the energy to make an ion. What type of ion? We're making a positive ion. So the first ionization energy means the energy needed to remove one valence electron of an atom. So this is the equation. X is an element. When X absorbs some energy, it makes an ion because you use the energy to remove an electron. So for this trend, we're only going to talk about removing only one electron. We will talk about the second and third ionization energy briefly in this lesson. So the first ionization energy values are found on table S for each element. So now we are going to do the same thing as electronegativity. I want you to look up the values of ionization energy for each element in period 2. Pause the video and resume once you have the answers. Okay, so here's the answers. For lithium, it is 520. For beryllium, it is 900. For boron, it is 801. For carbon, it is 1086. For nitrogen, it is 1402. For oxygen, it's 1314. For fluorine, it is 1681. And for neon, it's 2081. So what is the overall trend here? It is increasing across the period. So notice there's some exceptions, but there is an overall pattern. Based on the ionization energy values, thus higher ionization energy values means it's easier to move electrons or harder. Why? We know as we go across period 2, the effective nuclear charge increases. So the elements on the right of the periodic table have a stronger nucleus than elements on the left. A stronger nucleus will hold on to electrons tighter than a weaker nucleus. Therefore, you need more energy to move an electron from an atom with a strong nucleus than an atom with a weak nucleus. So if an atom have a high ionization energy, it means it is harder to move the electron. Why? Because it takes more energy to remove an electron from a strong nucleus, high effective nuclear charge, than a weak nucleus, low effective nuclear charge. So the question is, why ionization energy increases across the period? So again, we need to analyze the effective nuclear charge and the shielding effect. Let's look at oxygen, fluorine, and neon. At this point, you should know that the shielding effect is constant within a period. Each element has 2 inner electrons. So let's look at the effective nuclear charge of each element. Oxygen is 6, fluorine is 7, and neon is 8. So which element has the stronger nucleus? It is neon. So which element will have a harder time removing an electron to form a cation? That would be neon, because neon has a stronger nucleus. Therefore, you need more energy to remove an electron from neon than the other elements. Elements on the right have a stronger effective nuclear charge, therefore more energy is needed to remove an electron. So shielding effect is constant across the period. Now I want you to use table S and look up the ionization energy for each element in group 1. Pause the video and resume once you completed this. Okay, so here's the answers. Hydrogen is 1,312. Lithium is 520. Sodium is 496. Potassium is 419. And rubidium is 403. So the trend is that it increases from bottom to top. So ionization energy has the same trend as electronegativity. Check on understanding number 5, why ionization energy increases going up a group. Let's look at hydrogen, lithium, and sodium from group 1. We need to compare the effective nuclear charge and the shielding effect. You should know by now the effective nuclear charge is constant within a group. For shielding, hydrogen has 0 inner electrons, lithium has 2, and sodium has 10. So which element has the weakest shielding effect? That'll be hydrogen. So which element will have the hardest time removing an electron? That will also be hydrogen. Why? Because there's no inner electrons. There is no competition. Therefore, the nucleus of hydrogen is going to hold on to its valence electron much more tightly than lithium and sodium. Another way to think about this is that the valence electron of hydrogen is in the first shell, while lithium is on the second shell and sodium is on the third shell. The valence electron in hydrogen is much closer to the nucleus than lithium and sodium. So therefore, hydrogen is going to hold on to the valence electron much more tightly. Therefore, you need more energy to remove that electron. So more energy is needed if the electron is close to the nucleus. Less energy is needed if there's more shells or shielding electrons. And keep in mind, the effective nuclear charge is constant within a group. So now I want you to graph the ionization energy for the first 20 elements. Pause the video and resume once you've done this. Here's what your graph should look like. Learning check number 3. Which sequence correctly places the elements in order of increasing ionization energy? Pause the video and resume once you have the answer. Okay, so the answer is choice 2. If you don't have the trends memorized, you can always use table S and look up the ionization energy of each element. Learning check number 4. Which statement describes the general trends in electronegativity and first ionization energy as the elements in period 3 are considered in order of sodium and chlorine? Pause the video and resume once you have the answer. You should know that electronegativity and first ionization energy have the same trend, so they're both going to increase. So choice 3. Learning check number 5. Which electron configuration represents the element with the highest first ionization energy? Pause the video and resume once you have the answer. So the answer is choice 2. You can use the periodic table to identify what element you're looking at, then use table S to look up its corresponding ionization energy. Learning check number 6. From the list below, which first ionization energy will indicate the most reactive metal? Pause this video and resume once you have the answer. This is considered a very difficult question on the Regents, so I'm going to go over the answer. So the most reactive metal is the metal that loses the electron the easiest and the fastest. Here we're given the ionization energy, which represents the energy needed to remove an electron. So the more energy you need to remove an electron, the harder it is. The less energy there is, that means it's easier to remove an electron. Based on this analysis, the answer is choice 1. Because since it's easier to lose an electron, it is the most reactive metal. Now we are going to talk about the second and third ionization energy. The Regents are not really going to ask you this, but it's basically removing more than one electron, and this requires more energy. So let's look at an example, sodium. So this is the first ionization energy. It lost one electron by absorbing energy. The second ionization energy, you take the sodium plus 1 ion, you absorb more energy, and it loses another electron. The third ionization energy, you remove another electron by absorbing more energy. So here's more examples displaying the same trend. So this concludes the video lesson for today. Remember to do the Junipod homework.